Okay, then I can go ahead. Well, hi everyone. My name is Melisse Bonfand, and I currently work as a postdoctoral fellow at the University of Virginia. And I'm really happy to be here today and to get a chance to present you some of my work, because what I'm going to talk about is the achievement of 2 years of work within the ALMA-IMF consortium. So 2 years of looking into the data, reducing the data, analyzing the data, and facing all the problems you have to face at least once in your life when you're working with ALMA data. So we are now very close to be ready for the submission of the paper I'm going to talk about, and I'm pretty excited about it. So you're basically going to get some highlights of the results I will present in this paper before everyone else. So the paper is called "A Rich Population of Young High-Mass Proto-Stars Unveiled by the Emission of Complex Organic Molecules Detected with ALMA-IMF." So, oops. Yeah, so just to give you a bit of background on what the ALMA-IMF project is. So this is a large program conducted with ALMA, of which the full name is ALMA-IMF Transforms Our View of the Origin of Stellar Masses, because initially one of the main goals of the project was to obtain statistically meaningful results on the origin and evolution of the initial mass function. And if you want to know more about this particular thing, then I would refer to Thomas' presentation, our chair of today. So his presentation is on Friday, if I remember correctly. But through my presentation today, you will see that there are other science topics that can be addressed with the ALMA-IMF data, other than just focusing on the IMF part. So regarding the targets of the project, it targets 15 of the most extreme nearby galactic massive clumps that you can see identified with the purple stars here. And they were selected to probe different evolutionary stages, as well as a broad range of galactic environmental conditions. Here you have a list of the 15 target protoclusters that are classified as young, intermediate, or evolved regions based on the presence or not of ionized gas coming from H2 regions. And I've also highlighted in the different colors the regions that were barely studied before the ALMA-IMF project. So in terms of continuum data, we have 15 large mosaics towards the 15 target protoclusters, and we achieve a physical scale of about 2,700 AU towards each field. Here you see how the continuum emission looks like towards the 15 field at 1.3 millimeter. And what I wanted to highlight here is that all the small blue crosses you see are the continuum cores we extracted from these maps to build a core catalog of more than 800 compact objects. This core catalog and the method we use is presented in detail in this paper that was very recently submitted. So now, why do we need to build a hot core catalog based on this data? Well, the idea is to be able to increase the number of known hot cores in order to build a statistically significant sample of hot cores that we can study, investigate in details, and compare to each other in a homogeneous way, thanks to our ALMA-IMF data. And the idea is really to focus on the early stages of the high mass star formation process and its associated timescales that are still poorly constrained so far. So to give you an idea of how the spectral setup of the ALMA-IMF data looks like, here you see we have several spectral windows, both in ALMA band 3 and band 6. And we have the spectral windows that focus on specific lines, and I'm going to give you some examples here. So we have, for instance, a spectral window that focuses on H2H+ to study the kinematics of the regions. We have 2 spectral windows that focus on outflow traces, CO and SIO. And we have some broader spectral windows that contains plenty of lines of complex organic molecules, which are well-known traces of hot cores. The one I want to focus on today is this one, a spectral window in ALMA band 6 that contains 4 very well detected and strong transitions of methylformates. So methylformate is this species you see here. It's a complex molecule that is commonly detected towards high mass star forming regions. And for this project, I used this species to perform an unbiased search for hot cores in the ALMA-IMF data. So the advantage of using this line is that, as you can see in the spectral window, in most cases, the level of contamination from other species is quite low. So it's easy to identify the 4 methylformate lines. They are strong. They have the same shape and more or less the same intensity. And they also have a similar upper energy level, which suggests that they're tracing the same gas with the same physical conditions. So here the idea is to look at the spatial distribution of methylformate towards the 15 ALMA-IMF protoclusters. And for that, we look at moment zero maps here. From these maps, I developed an automatic method to extract the sources using a source extraction algorithm that is called GEX2D that is developed in Bordeaux. And it basically works with the second derivatives to identify local maxima in these maps. So this is what you see marked with red crosses here. These are the local maxima that were identified in the map. And it's basically the peak position of the methylformate emission that we will consider as potentially hot core candidates if they satisfy two criteria here. So the first one is that the local maxima have to be detected with a signal-to-noise ratio higher than 2.5 in the maps. And then the second one is when we check the spectra extracted towards the position of like each peak position here, we make sure that the methylformate lines are indeed detected above a 3 sigma noise level to avoid false spurious detections. And once we have our list of candidates, then the algorithm performs a Gaussian fit to measure both the flux of the methylformate emission and the size of the emitting region. And here you see, for instance, with the red ellipses, I show the deconvolved sizes. So in terms of statistics, at the end, we were able to identify in average 5 methylformate cores per region. And this gives us a total of 76 cores that are potentially hot core candidates in our sample. So most of these cores, if I go back to the example I showed just before, most of these cores are individual objects that are rather spherical and compact. And by compact, I mean here a few thousand AU. But we also have 2 cases of fully isolated objects where it looks like we have a single methylformate blob standing alone in the field of view. And we also have 5 regions where we have much more extended structure of methylformates that goes from 5,000 to more than 10,000 AU. So if we look at the general size distribution of the methylformate emission for all the cores in the hot core candidates in our sample, so if you look at the red histograms here that shows the sizes that are deconvolved from the beam size, you see that the hot core size range is from, let's say, about 1,000 AU to more than 30,000 AU with a median size of 2,300 AU here. So if we want to look at the same distribution, but for the mass of these cores, then we have to make some temperature estimates first. And for that, we look at how methylformate is formed into these regions. And for this, we look at the predictions of chemical models. So if we follow the evolution of the green line here in this plot that shows us the formation of methylformate, and in particular, the green dotted line here that shows us the solid phase abundance of methylformate, you see that methylformate is formed on the surface of dust grains in a temperature range that goes from 15 to 30 to 40 Kelvin in this chemical model. And then when this dotted line drops here and the solid one that shows the gas phase abundances increases, this is where thermal desorption happens. And this in the chemical model happens in between 120 and up to 160 Kelvin. So based on this, we distinguished 3 types of objects in our sample that are associated to methylformate emission. And the first type of these objects are the hot core candidates, so the peak we find in the methylformate moment 0 maps, which have an emission size that is larger than the continuum size. And for these objects, we assume that we are probing really the inner hot part of the emission. So we are in this temperature range here where thermal desorption happens. And we consider we are at a temperature that is around 150 Kelvin. And if I plot here the size of the methylformate emission against the size of the continuum emission, this is going to be the case for all the sources we see here above this dotted line. For the other sources that are just below the dotted line, these are the sources for which the emission size is more compact than the emission size in methylformate, is more compact than in the continuum emission. So we assume we are probing a slightly outer part of the envelope of the source that is also slightly colder. And so we assume a temperature of 50 Kelvin for these objects. And finally, we have other objects, other continuum cores that fall into the very extended emission of methylformate that we assume that are still in a gas that is warm enough to form methylformate and for which we assume 35 Kelvin. So now that we have these groups of temperatures, we can estimate the mass of our objects. And this is so the temperatures I just showed, we used to build the white histogram here that shows the mass distribution of all the cores that are associated with methylformate emission. And we compare this mass distribution to the one you see in blue, which is the distribution of all the cold continuum cores that are not associated with any methylformate emission and for which we assume a cold temperature of 20 Kelvin. And so if you look at the distribution, the white histogram here, you see that the cores we have that are associated with methylformate emission range in mass from 0.3 to more than 200, to more than 260 solar masses, with a median mass of about 6 solar masses, which is slightly higher than the median of the blue distribution here, that is more around 2 solar masses. Another thing, if we look at the red curve here, that is the cumulative fraction of hot cores versus the number of continuum cores, we see that above 44 solar masses, all the cores that we have in our sample are associated with methylformate emission. And if we look at a slightly lower threshold here of 20 solar masses, then 90% of these cores are associated with methylformate emission. So now if we want to discuss a bit more the nature of the sources we are looking at, we can look at this plot that shows you the mass of the objects of our potential hot core candidates that is plotted here as a function of the size in the emission, in the methylformate emission. And what we see is that we have all this group of sources here with masses that are typically above 20 solar masses that are most likely going to form stars with a final mass that is higher than 10 solar masses. And in terms of size, you see that the size ranges from 1,000 AU to up to more than 10,000 AU. So this is typically the sizes and the masses we expect for hot cores from the values, typical values we can read in the literature. So this group are excellent hot core candidates. And then we have another group of sources here, lower mass objects that typically have masses that are between 1 to 10 solar masses, let's say, which we would like to call hot corino candidates. But when you look at the size distribution here, you see that it goes from 1,000 to, let's say, 5,000 or 6,000 AU, which is much more than what we expect for typical hot corinos. So the nature of these sources is still unclear. And it is actually possible that with the resolution of our data, we are not sensitive to hot corinos in our case. So time to wrap up and to summarize what I said just before. So methylformate emission is detected towards all the 15 ALMA-IMF proto-clusters. And we saw that in most cases, it traces compact objects with rather spherical emission, with sizes that range in most cases between 1,000 to 6,000 AU, with just 2 outliers with 8,000 and more than 30,000 AU. We have an average detected 5 methylformate cores per region, except for 2 cases where we have isolated cores. And this leads up to a final catalog of 76 star-forming cores that represents about 9% of the total continuum core sample we have in the ALMA-IMF data. We estimated that about 2/3 of the 76 cores are new detections, and about 30% of them are excellent hot core candidates because they have masses above 20 solar masses. And for the rest of the sources, their exact nature still needs to be further discussed. They might form at the end intermediate or low mass stars. Here, I just wanted to show this slide. This might be not completely up to date. Maybe a few papers are still missing, but just to give you an idea of all the ALMA-IMF papers that have been published already and all the people that are currently working on papers. And I would be happy to take any questions if you have some now, or otherwise do not hesitate to email me or visit our website and have a look at all the great work that the ALMA-IMF people are doing. And I think, yeah, I should be on time. Thank you for your attention.